Next, let's see how to represent negative and positive integers in a C++ program. To define a positive integer, we will declare a variable called c of type int and initialize it with value 5. To define a negative integer, we will declare a variable called d and initialize it with value -5. Now, if we print 5 and -5 in binary representation using std-bitset, we will see what will be the binary representation of these two numbers. So we know 5 in binary is 101, so all the most significant digits are expected to be 0, which is how it is. But we don't know what the 2's complement of 5 is. So we see that -5 is this big binary number, but we are not sure whether this is equal to the 2's complement of 5. So to verify this, I've broken down the computation into different steps. So first we will compute the 1's complement of 5. So in this line, we're computing 1's complement of 5. To compute 1's complement, we can use the tilde operator. So what the tilde operator does is, it flips each bit of C. So all the 1's are flipped to 0s and all the 0s are flipped to 1. Then I'm printing out the binary representation using 32 bits. So let's execute this line. Let's see what is the 1's complement of C. Now notice all the most significant digits in C were 0s. Now it has flipped to 1's. And the last 3 digits was 101 and now it's flipped to 010. So this is the 1's complement of 5. Now if we add 1 to the 1's complement of 5, we should get the 2's complement of 5. So let's add 1 to 1's complement here. So again, use tilde to flip C, then add 1, then convert the result to a binary using std-bitset. So if we execute this line, we should see the 2's complement of 5. And we can then compare whether that is equal to the binary representation of -5. So the 1's complement of 5 plus 1, which is equal to this binary number. Now notice this is exactly equal to -5. It is difficult to compare a 32-bit number. We need to compare each digit one by one. So instead, let's see whether we can add an if condition and do the same comparison. Here, what I'm doing is, I'm comparing whether 2's complement of C is equal to D. If 2's complement of C is equal to D, we should see this print statement which says 2's complement of 5 is equal to -5. So let's see whether we see this. Let's continue the execution. And notice now 2's complement of 5 is equal to -5, which means negative numbers in C++ are encoded using 2's complement representation. This happens by default. You do not have to know how this happens in the background. But we've seen the computation happens by first computing the 1's complement and then adding 1 to it. Now, the next line is checking whether 2's complement of D is equal to C. So what this is checking is, can we take the 2's complement of a negative number and get the positive number? So we've seen before, we can take the 2's complement of a positive number and get the negative number. What this is checking is, can we do the opposite? So now let's execute this line. If 2's complement of D is equal to C, we should see this print statement which says 2's complement of -5 is equal to 5. Let's see if this is printed. Okay, now notice 2's complement of -5 is actually equal to 5. So what this says is, when we take 2's complement of a number, if the number is positive, we get its negative equivalent. If the number is negative, we get its positive equivalent. So 2's complement is really powerful, and we will use this property when we do 2's complement arithmetic. So next, we will see how to represent the maximum 32-bit value of an integer using binary and hexadecimal format, and then we will print them. We know that even though we print a binary or hexadecimal, the print should be an integer. So again, through these statements, we will see what is the maximum value a 32-bit integer can hold. First, I will show you a different way of representing a binary number. When the binary number has a lot of bits, it's usually good to group them into separate groups. Here I'm grouping bits into groups of size 4. So each group is separated by the next group using apostrophe. The first group is 0, 1, 1, 1, and then the remaining 7 groups are all 1, 1, 1, 1. So by grouping binary into smaller groups, it's easier to read and write the binary number. Now let's see what is the maximum value that can be stored within a 32-bit int in hexadecimal. Hexadecimal is far more simpler. We see the first digit is 7, followed by 7 Fs, right? So it's FFFF, FFF. It's not only easier to read and write, it's also a much more cleaner way of representing the integer in the program. So now let's continue execution and let's see what is the decimal equivalent. We've already seen this before in the slides, so it should be 2 to the power of 31 minus 1, which is 2,147,483,647. Now notice again, as the number gets bigger and bigger, the hexadecimal is a more convenient way of representing the integer. It's easier to read and write and easier to also to maintain the code. Now next, let's see how to programmatically query the range of a data type. To do this, we can use this template function called std numeric limits. So to use the template std underscore numeric limits, you need to include a special file which is limits. So if you do hash include limit in your program, limits in your program, you can call this special function std numeric underscore limits, which is again a template. It takes a parameter. Here the parameter says what is the data type of which we want to query, either the maximum value, minimum value. There are other things that we can do with numeric underscore limits. Here I'm restricting to querying the maximum and the minimum so that we can print out the range for both int and an unsigned int. So when we execute these 4 lines, we should see what is the range of both signed and an unsigned int. So let's continue again. Now notice maximum 32-bit integer is 2 to the power of 31 minus 1. Maximum unsigned 32-bit is 2 to the power of 32 minus 1. Minimum unsigned int is minus 2 to the power of 31. Minimum signed int is minus 2 to the power of 31, and minimum unsigned int is 0. So we don't have to actually remember the range of these different data types. We can programmatically query it using std underscore numeric limits, std numeric underscore limits. Now let's see an example of how to use this special template within a program. Here I'm declaring a variable called variable called b, which is of type unsigned int. It's initialized with a hexadecimal representation. So the value is 0x dead beef, DEADBEF. And the question is dead beef a signed or an unsigned literal? So one way to check this is, can we look at whether this value is greater than the value that can be stored within a signed integer, the maximum value that can be stored within a signed integer. To do that, I'm checking it using this if condition, wherein I'm checking whether dead beef is greater than the maximum value a signed int can hold. To query what is the maximum value a signed int can hold, I'm again using std and numeric underscore limits, passing signed int as the type and querying what is the max value. Now if we see this print statement on the console, we know that dead beef is not a signed literal, it's an unsigned literal. So let's continue the execution and let's see what is dead beef. Again, notice it's far more easier to read and read this integer when it's represented using hexadecimal format. In integers, it's a really big number. And second, we also see the print statement here, which says dead beef is outside the range of a signed integer. So we know that dead beef is not a signed literal, it's an unsigned literal. Again, so we used std numeric underscore limits to query what is the maximum value a signed integer can hold. We will see further, we can pass other than integers, we can also pass floats, doubles to this program, and we can query the range of different data types using std numeric limits. Next, in the next video, we will continue with different other modifiers for integers. We saw signed and an unsigned int in this video. We will continue with short and long in the next video. We will see what are the ranges of using a short or a long integer. And we will also see examples of integer overflow. Um, Thank you.